Right. Our next speaker is Chris Hakkenberg with Rice University.
Is there some animation?
Title is Monitoring 2 Decades of Urbanization in Houston from Space.
Today I'm going to be talking about some work I've been doing with the Kinder Institute here, as well as the Department of Statistics here at Rice, that's using satellite imagery. You can see one here to look at the dynamics of Houston's growth. So I'm really going to be talking about three things today that I want to focus on. First is an approach. So this is a series of algorithms that we generated to automate this process of converting digital reflectance numbers into usable land cover data. And what's interesting about some of these approaches is this overcoming some of these trade-offs between fine spatial temporal resolution and extremely large extents. Second thing we're going to be looking at today is the product itself. It's freely available. It's ready for analysis. And so I think there's a lot of interesting opportunities in collaboration to use this. And finally, what this says about the extraordinary growth of Houston itself. And using satellite imagery, in a sense, as an unbiased eye in the sky, so we can kind of look beyond some of the ground data and actually see empirically what's happening on the ground. So here is the area that we're talking about. And so when I say that I'm characterizing land cover change from 1997 to 2017, what I mean is how has the Earth's surface changed in terms of land cover? And by land cover, what I'm talking about are these thematic classes. You can see the 9 right here. The first is this kind of barren sand, which could include a construction site. We've got 4 categories of developed or urban land that vary in terms of intensity, the darker red being more concentrated urban cover, cultivated crops, agriculture, grass, forest, and water. So there are these 9 classes. We're looking at this time series of maps over 21 years. The resolution is 1 year, so we're doing it every year. And the spatial resolution is 30 by 30 meters. And finally, the spatial extent is 35,000 square kilometers. Now, just to give you an idea of how insanely large the greater Houston area is, I superimposed it on 2 larger urban areas. Now, mind you, this isn't all urban. It includes some of these outlying counties, but still, look here at New York, where the Houston area goes up into the Catskills, all the way down to Philadelphia, and includes almost the entirety of New Jersey. The same in Boston, up here to the White Mountains, all the way down to Long Island. So think about this when you're commuting home today, the enormous size of the Houston area. So what we're doing here is we're using Landsat imagery for the Landsat satellite. It's actually a series of satellites that have been in the near orbit since 1972. And we're producing some of these here. This is some false color composites of the Houston area. And just to give you an idea of some of the data volumes, here we have that original image. So that image translates into about 60 million pixels. You're just going to see a running tally down here so you can keep track as we go. So each one of those scenes, as they call them, has 6 different spectral bands. Because it's an enormous area, we need 4 different scenes to cover it. In any 1 year, we have between 3 and 7 images. We have 21 years. And for each of these, we're using a random forest classifier. It's giving us posterior predictive probabilities for each of the 9 classes. Each of those are based on 1,000 random forest votes. We're up to 13.8 trillion here, and that's not even getting into bit depth and other sorts of things. So it's a decent-sized data set, certainly not the largest I imagine some people here work with. But so how we're doing this is the kind of first algorithmic innovation is automatic adaptive signature generation, which allows us to automate this really, kind of otherwise very tedious process. To run you through it really quickly, we have an image from date 1. We have a reference from that same date that comes to us from the National Land Cover Database from the USGS. Then we have an image from date 2 without a classification where we want to make the prediction. So what we do is we use this to essentially find stable pixels. In other words, land cover has not changed in between the two dates. And then we kind of take away the extremities, we call it for edge effects, and we find those pure pixels which have not changed, which we can then use to train the model automatically to produce this classification for date 2. And as you can see, the land cover changed quite dramatically. Secondly, and this is just in press now, is an ensemble classification approach. This also using posterior possibilities from the random forest, where in this example, we're taking 3 images in a year. As you can see, the images are often very noisy. Here we have algorithmically delineated clouds, which we've taken out, those black gaps. Here we have scanline corrector error. Here we have atmospheric contamination. So we put these 3 together, and you can see in this 1 year, there's actually quite a bit of noise and data gaps. So what we can do is we can use this data that remains to make the most robust possible classification for that data. And then we go through one by one and use those individual images to classify just the area within those gaps. We merge the 2, and I can get into more detail later about how I merge those, and so we can effectively fill the gaps so we have a spatially continuous map. The final part, this is currently in review. This is just one quick example of various spatial temporal filtering algorithms that we developed to be able to make the map time series consistent in space and time. Here, through time, essentially we're trying to control for spurious fluctuations, anomalies for a single pixel along the time series and try to smooth those out. In this case, it's a Gaussian smoother. So on to some results. This is just kind of, you can give a quick visual examination. This is less urban and more urban, some areas around Houston to kind of show you some zoom-ins of what the classification looks like. We also, of course, this is a time series. So what we're interested is in change through time. So we can look at it through time. Here's the Woodlands that is developing. You'll see the year on the bottom, which is pretty extraordinary how that's changed. Of course, you can put these all together, and you have some interesting eye candy gifts. These are the same map. They're just running at different speeds. You can see the year at the bottom here. And again, extraordinary to think about how many organisms and communities grow, humans being one among them. And the next part of this project is really thinking about these spatiotemporal morphologies, about how we're growing and why. What are the socioeconomic and other constraints, environmental other constraints to growth, which is giving rise to these very interesting patterns. So another product that comes from this is looking at year of conversion. So here again we have the Woodlands, and here is Cinco Ranch. So what we can do is we can find the year of conversion, give that a color ranking, essentially red to blue from 97 to 17. And so we can see the manifestation of that temporal process. And in this case, you see the Woodlands is clearly growing from east to west through time. Cinco Ranch, you see more of a concentric growth that's coming from all directions. Again, ripe for various types of spatial quantitative analyses. A map is only as good as its accuracy. There's a tripart accuracy assessment that we conducted. This is one of them, perhaps the most robust, where we use a series of independent aerial imagery to be able to test this. Without getting into details, we're very happy with the results, seeing between 78 and 94% accuracy. The reason it's not higher in many cases is you have edge effects. or you have confusion between very similar classes, between different developed classes, where one could be 49%, another could be 50%, and it could go to either class. So in terms of the growth of Houston, we also have some interesting results. First, if you lump these developed classes, we see the addition of 2,000 square kilometers in 20 years of pavement, of rooftop, of development. Again, I love giving context. So here is Central California. If you look at that development, that's really the central square here. It encompasses San Francisco, a lot of the peninsula, Oakland and Berkeley, and in fact the entire bay itself, which has been developed, which has been paved in 20 years. Pretty extraordinary. So among all of those areas converted, according to data from NOAA's Coastal Change Program, we see that 14% falls in designated wetlands. And conversely, if we look at the FEMA 100-year floodplain, which has been a moving target, but the one of record, we see that 20% of that development happened in the FEMA 100-year floodplain. So, drive your own conclusions from that. So here's just a few quick examples of the specific jurisdictions that we're looking at that have the most pronounced change in terms of the FEMA floodplain. Here, the top row is 1998, bottom row 2006. Here's the full jurisdiction. Here's just that proportion that's in the floodplain. You see in Greatwood, almost the entirety of the floodplain has been converted, and not just converted, but converted to this highest density urban. We see the same thing for Sugarland, although that is quite a larger area, so not as much of a total proportion. Another interesting facet of this work is thinking again about change through time of these time series. These are the kind of linear growth rates. I draw your attention to some of the deviation from those growth rates. We can plot it here, and excuse me, this plot is not rendering well on the screen, but you can get the idea that this is the linear growth rate of all developed categories, and this deviation from that growth rate, I think, says a lot about the nature of that growth. And it doesn't coincidentally peak at 2006 and start to drop precipitously 2007, 2008. Of course, these are the dates of the onset of the Great Financial Recession. We see these trends coincide quite well with other socioeconomic demographic factors like GDP, housing price index, and population in the 13-county region. So I'm just going to conclude here. Not saying anything new here, but just to remind everyone of kind of what I've just been talking about. The first is this algorithm, a set of algorithms that we're happy about in various stages of review and publication that combine this adaptive signature generalization to handle all training data selection automatically, the Ensemble classification for gap filling and dealing with data errors and noise, and finally a series of stabilization procedures in space and time. What this has allowed us to do is kind of cut through and overcome some of these traditional trade-offs between spatiotemporal resolution and extent. Next, the product itself, multi-decadal, multi-scene, and annual at a 30 by 30 meter resolution. It's, for various reasons, you could say that this is unique in the literature. It may be interesting for a larger crowd to think about how we can interpret things like periodicity, abrupt transitions, and time lags in that growth. And that's why you need an annual series and not just maybe what the NLCD has, which is once every 5 years. You're not capturing that temporal granularity that is really critical to some of the questions the people in this room and elsewhere might be asking. Finally, it's been validated, and we're happy with the accuracies in line with what you see in the literature. So Houston, yes, 2,000 square kilometers, the entire Bay Area has been developed in 20 years. 20% of that is in 100-year floodplain, and 14% in wetlands. So this is, again, this is up now and freely available on the Urban Data platform. I invite you to go look for it. There's lots of amazing data out there. This can be downloaded in a GIS-friendly format. And we've already had a lot of requests, and we're working on various projects in socioeconomics, development conservation, flood planning, and urban hydrology. And with that, I thank you, and I'll take any questions.
Have you heard about how cities might, or growth of cities might follow a metabolic change law? And if you found that applied with different cities, like I imagine Houston and Austin's rate of growth would be wildly different.
Yeah, it's a good question. So with this project, we haven't done that. So there are a lot of interesting studies that are looking at various constraints to growth, environmental, topographical. We clearly don't have that. So I think that the next stage of this study will be to characterize specific modes of growth. For example, leapfrogging, where we see various satellite communities emerge with space in between, or edge expansion, where you just see the growth from that focal area extending out. A lot of these have to do with public transportation and infrastructure, as well as underlying economics, cultural attitudes, planning, policy, a lot of these different things. And so there are interesting studies that compare different cities. One of those uses Houston, and perhaps not surprisingly finds that Houston has a lot of sprawl. So go figure. But one thing that's interesting from this is that we're finding that study was done in the mid-90s, that a lot of the new development in Houston is actually a third urbanization morphology, which is infilling. So we're actually seeing, like in Harris County specifically, we're seeing a lot of infilling. And sometimes maybe that comes at the expense of a park, or probably more often an empty field. But we're seeing some evidence of densification. So that's something to be thinking about going forward too.
I had a quick question. How did you define what you were going to call the Houston area? I've spent some time in the Bay Area, and it seemed a little bit of a stretch to say Houston extends to the Sierra Nevadas. I think of Houston as sort of the whatever the Grand Parkway maybe area.
Sure, yeah.
Pick.
So Greater Houston here is just defined specifically, and we actually went kind of tormented over this, by the HGAC. So the Houston Galveston Area Council defines the 13 counties which are included here, which I will not be able to recall by name, as the Greater Houston area. And so some people use the Metropolitan Statistical Area. I think the primary three counties that we're talking about is Montgomery, Fort Bend, and Harris. These outlying counties, we really wanted to be sure to capture, because a lot of the growth going forward is going to be happening there too. So again, when I overlay those, the caveat is that that central area is still a lot smaller than the entire 13-county area. But we figured it would be better to err on the side of too many counties than on too few, because again, we want this product to go forward in the future and for people to add on to it. And so might as well start with the 13-county HGAC.
Hi, thank you for the presentation. This analysis is pretty useful in understand the change of the land use. But I have a question about one possible direction of your research is that as the time goes, there are some change in the characteristics or more specifically the variables in terms of the community survey or the census data, so that although the size changes, but some gentrification, de-urbanization also happens, not so obviously shown in the change of the land use, but in how this land are used by different people from different classes or economic classes. So I'm wondering, have you considered that kind of more qualitative research of different areas of Houston to improve your space studies of urbanization?
Sure. Thank you for the question. So if I'm understanding you right, I think it primarily comes down to this distinction between land cover and land use. And I think that land cover is something that is a kind of biophysical characteristic of space that we can characterize with a satellite. And the questions of the types of data that you're mentioning, those sorts of questions, I think, are maybe better characterized under the broader title of land use. And there are distinct correlations between the two. And so we are commencing collaborations to look at some of those. And this part of the project was simply to use satellite imagery to characterize those changes. And so we simply can't get at some of those more fine-grained changes. But through modeling, I think that is very possible. So using like a lot of the data that's on the Kinder UDP, we can start to really give some life, I think, to what could otherwise be seen as kind of a cold observation of the Earth's surface.
Thank you very much.